Okay, so we will start with the MATLAB first. So you remember that last week we had the tutorial, sorry, the presentation by the visitor lecture, and because of some technical issues with the Zoom, we had to move to Teams, and we had recording for 1 hour only. But still, if you go back to the last year recording, you will find more detailed recording that actually for 2 hours. I highly advise you to...
So you think you know Wix, do you really?
Wait a second, let's finish.
First up, we've got shaking.
Okay, so in this tutorial, which lasting for 2 hours, I tried to make it compressed for you. Just remember that here I only try to make you break the ice to know how to start the code and how to change the parameters and how to get the results. For certain details, more details issue, you can go back to these videos. So again, if you remember that we're working on the project. So if I get to go to the assignments, I will go to the project. Okay, that's the mini project. And you remember that last week we covered the first task, the spool on the truck, and the last virtual lab. Today we are going to work on these two. Now, mostly the difference between why we kept this one to the second session, because they almost the same scenario. We're going to have pendulum need to work and hit something or just moving. So I can start with the first one, which is a pipe suspended on the forklift. So what they're going to have is concrete pipe, have a mass, have a radius of gyration, and it's going to be connected by a strip or belt on the forklift. So while the forklift is moving, then it's going to stop. What's happened to the pipe? It starts to swing. So in the swing, it's going to work as a pendulum. The first case is that we consider that this part not going to have any slipping. It's going to be stay in position. The second case, when you're going to stop, this will start to slip. So it's going to move forward while you are going to have the movement. The second example, virtual lab, is going to be about a block, have a mass, have a height, has a width, has a depth, and it's going to be hit by a pendulum. So usually when you're going to hit it, the highest the mass of this pendulum, the further distance that this block is going to be pushed for. The position is going to be something similar, and that actually I had this example in my Teams. Okay, go to here. That's why I put this photo here. You remember that we had one of the examples. No, I think that I add the other one somewhere. Something like, you remember the bar that we said when you're going to hit it, it's going to be slip, but it's not going to be flip. And we need to find what will be the height for the position of the impact. We did that question in the quiz preparation last week, 2 weeks ago, actually. So the same scenario will be here. So the second part of this experiment is going to be what height we're going to have to hit the block to make it flip instead of slide. And we're going to have a look on this one very soon. So again, I remember that you did what the video asked you to do, which is getting the master the file for me. I do it one by one. So once again, to do it one by one, I'm going to download this file now. Okay, go to the downloads, and we're going to extract this file. Okay, so it's something like, I always believe in it, that if you would like to open the file, go the long way, don't go for a short way that you don't know it. So once again, if I get to double click on this file, let's investigate what we have inside. You can see that we have a PowerPoint here, like what we had last time. So if I double click on this one, you will find out that it will contain some of the free body diagrams, similar to the case we had last time. So once again, you can get these images if you want. Just select them, Control C, and you can paste them as an image, and then you can put this image on your report. It's much better than have the individual parts on it. You can add actually a text on that and improve that. For example, you can change that. You can put a textbook here and write down what is the shape, and when you do the select, it will be selected as well. So these are the 3x diagrams all being applied, and you can, as I told you, copy that and paste it in your work, except for this one, because you're going to get that from the actual simulation. Okay, and in this experiment, we're going to have two things. The first one is going to be the Simscape, and the other one is going to be the Simulink. And actually, there's a difference between the Simscape and the Simulink. Simulink is something you can program. You can make this a block by entering your code for the MATLAB. Then you can make it as Simulink block. Then you take it to the Simulink model and connect it. For the Simscape, you're going to use your ready-made blocks, and you will get a similar results, and we will see a comparison between the two results. The second scenario we're going to have is that the pendulum, while it's going to be swing, is also the connection point start to slide. And we're going to do it for the block and for the roller, as you are going to see next. So again, for you, you are going to copy this file, this folder, and put it in your directory that you make, which is the BH in the C or the BH in the document if you're using the Mac. For me, I'm going to use the online MathWorks. So now I already did that yesterday. I unzipped this file and I brought it to my drive, the MATLAB drive. So you will find it available for me here. Again, there's no problem that you use the online version, because it's up to you. And you can see that the pi pendulum is already here. So now I'm going to open that on the MATLAB online. Once again, that's me. For you, you can use the one that you downloaded on your computer, which is sometimes going to be much easier to manipulate, unlike this one. Okay, so it's uploading. Okay. So now we can see that I cleaned my window yesterday, but usually I prefer to re-clean it. So I'll write down clear here. Okay, and CLC, just to get a fresh window. Now I will look for my file here. It's not the pendulum, that's a different one. That's the pi pendulum. So I can double click on that to open the folder. And I have to be sure that I have the pipe underscore pendulum has been uploaded here. How to have it that way? Simply you go to, sometimes it's going to be a drop list, sometimes it's going to be the 3 dots, and you can group by type, and you will see them like that. So you can see that this is the text, this is the MATLAB codes, and these are the Simulink codes. We're going to start with the task number 1, which is the Newton derivation for the equation. Once again, I don't like the double click on the online version, so again to right click and again to this one is going to be open. So now this will give you the derivation for the equation we're going to have. Remember, never run that from here. I'm going to go through it step by step to generate some of the data on the workspace, data and files. So again, you remember the 3x diagram for the pendulum. We're going to have the theta angle. It's going to have a different value for the theta dot, which is the omega, and theta double dot, which is the alpha. How the parameters of the pendulum is going to be changed. First, the mass. Second, the length. Third, the theta. And all this stuff will affect the reaction forces we have at the point O. And that's what we are going to try to find with this code. So first we define the sum of the simple variables. So we have the L, which is the length of the yellow strip. We have the R, which is the radius of the pipe. The IG is the moment of the inertia we have for the pipe. the G, which is the 9.81 meter per second square, and the M is the mass. They done all that. Just click anywhere here and click here to update this section. Okay, so you can see that the list of the parameters has been created in the workspace. Just remember something. Here, the yellow line is representing a belt or strip. That means its mass is going to be negligible. What will be the case if I'm going to have a heavy bar that have a considerable weight to be used here? What will happen? What will be the main change we are going to achieve? You remember the example we had for the benzonium? What we had in this example, we calculated the IG value because we are going to have two sections. Each section is going to have a different value for the G centroid. And we use that to calculate what will be the centroid for the whole shape. But here, as long as the weight of this one is not important, so we're going to consider that the centroid of the whole system is going to be the center of the circle. Now, the second step is compute the acceleration of the pipe, okay? And to do that, we need to find the theta double dot, which is the alpha. So again, we're going to have the equations for the XY position, the velocity and acceleration at the pipe center G. So these are the equations for the position, for the velocity and for the acceleration. And we're going to make that actually more details, might make them as a MATLAB code. And actually you can put the mouse anywhere, and you will see that the blue is going to be activated. So I'm going to click on that, and you will see that more files are going to be added in your workspace. Now, this is the equation we're going to work on. Now, that's a free body diagram. We need to find the reaction Rx and the Ry. And to do that, we're going to add the free body diagram, and we're going to have the kinetic diagram to calculate the equation. So you remember that the equation says that in the free body diagram, forces are going to be equal to the kinetic diagram forces, which are equal to the mass multiplied by the velocity, by the acceleration. This acceleration can be linear in the case of the linear forces, and in the case of the momentum is going to be the alpha, which is the angular acceleration. So now we got the equation has been prepared. This equation has been changed to look like that. And that's for the momentum. For the moment, it's going to be the IG multiplied by the alpha, as you remember. It's going to be equal to the sigma of the moments around the point G, which is going to be the Rx by the horizontal distance, so by the vertical distance, and the Ry multiplied by the horizontal distance, as you can see. Now we got this equation has been created. Again to update that. It's already been calculated, but this is the equation we're going to work with. Now for the pause and ponder, we're going to have now three equations to calculate the three unknowns, which is going to be the alpha, the Fx, and the Rx and the Ry at the point O. Okay, which going to use actually this three equation 1, 2, and 3. So why we need the three equations? Because we have three unknowns. If I'm going to have four unknowns with three equations, this will make it very hard to be done. So again, I'm going to activate that to activate more of the parameters on my table. Now we're going to solve for the unknowns, which once again going to be the Rx, Ry, and the alpha, and all the equation for the force in the X direction and the Y direction has been represented here. Okay, and again, I'm going to update that. Again, I'm not explaining what do you have. You will need to find that yourself. You can see that all the equations are available for you. I think that you can simply, you can copy these equations very easy if you would like to take them to your, wait a second, Control C. Let's see if we can get that here. No. Okay, so yeah, I think I shared something yesterday with one of your colleagues about the software I'm using nowadays for snapshot the screen, which is quite better than the one that we have for rather than the print screen that you usually use. Copy link. So I found that actually this software is quite free for basic use, and it's very simple. It's all going to have a bar on the side here, contain the camera and the video camera. So you can simply click on the video camera, select the area you want to record, and start to record the video for you. You can download it and use it. The other way is take the normal camera, take a snapshot with very high quality of the image. And as I told you, it's much better than the the FN print screen. And you remember that this will be the quality of the work we're going to have, and then you have to trim it. For the software I told you about, it can take the specific area. Also, it's have higher quality when you, for example, take a snapshot for an image or take a snapshot for a book page. Okay, so once again, we go into the pose and the pounder. What we need to do here, we have three equations shown below, the solution for our unknowns, which are the alpha, the Rx, and the Ry, as a function of time, of course. And we're going to use nonlinear ordinary differential equations to be solved with the MATLAB. Now we're going to convert everything we've done earlier to a Simulink block, which is the block I showed you earlier here. Okay, so by the next click, I'm going to create this block. So you can see these are the commands to make a Simulink block. Okay, you give it a name, you give it the input and the output parameters. Okay, and just make it work. So again, I'm going to click here. Even the color you can define it by putting the code color for the Simulink. So clicking here, and this will open a new window, which is going to be the Simulink block. I can put in my Simulink model. Okay, still calculating, it's quite heavy. Okay, so you are going to have the block is made here. Okay, so if I'm going to get close to okay, now how to see what's written here, you can simply do as the normal thing, just expand it. So you can see here that we're going to put the inputs like the amount of the inertia, the length, the g, the mass, the radius, the theta, and the theta dot. The output is going to be the theta double dot, the Rx, and the Ry. This will be put within a model for the Simulink, and that's what we're going to see in the step number 2. And the next step, we're going to check that. So click on that. Okay, now this will be simulate our model like what we've done earlier. So once again, we're going to define the parameter values we talked about in the part number 1. First, the G is going to remain the same unless we're going to change the elevation of your position. Change the L, you can change the R, you can change the mass, the parameters, pipe, linear, in meters, also other less radius actually. Okay, so you can change all these parameters, including the theta, and the theta dot is equal to 0. That's the initial position. So the part is not moving. So we consider that the theta dot is going to be equal to 0. Define the parameter values for our model 2, part 2, when it's going to have the movements to be done. So once again, that's our part. We're going to decide the radius to be 0.15, and we're going to put all the parameters to be created. So once again, I'm going to update these files by putting this here and click the blue. Now, these values has been changed in these tables. So once again, I can change that once again and update it. So I will make this one as 0.25. I will change this one to 0.14. Okay, and change this mass to 700 instead of 750. And now, because I made these changes, I need to update my Simulink model. And to do that, you can see that this one changed to a hash lines. I have to click on it to make it blue again. Okay, now I will do the same thing for this one. And then we're going to have the Simulink model is ready for you. We're going to operate this one now and run it and see what will be the output, which is going to be something like that. You can make a use of that, and you can take some of the discussion points by analyzing what we have in the description. So if I'm going to execute this section, it's going to open the Simulink for me, and then we can run it to find what will be the results. Remember that in this scenario, it's only going to be swing without having any friction or movement to the top point, which is, okay, now this point is stationary in the first scenario. Okay, so now we have the tables are empty because we didn't run any simulation yet. I'm going to close this one temporarily, expand that to the size. Now you can see that we have two blocks. The first one is going to be the Brain Newton model, where we put the Simulink block that we generated. And the other one is going to be the Simscape model, which is a little bit more advanced process. So that's the one that we have. That's the block that we generated from the first step. Okay, you can see that these are the parameters I'm going to put, which is going to be mainly a constant. The one that are going to be changed, like the theta, is going to release from 35 degrees, but it's going to be start to swing. So it's going to be, for example, negative 35, then we'll go back until it's going to reach 0 at the end. So this will be a changeable value. So again, to make it as a feedback for the system. The same thing is going to be for the omega. So that's the calculation for the omega is the integrator 1, and that's the integrator 2, which is going to be for the theta itself. Okay, and the results will be coming from here. So I'm going to run this section first. Okay, once again, we see the things from the bottom. And I'm going to bring this one to the front. And you can see that that's what will happen to the pendulum. When we stop the forklift, it starts to swing until it's going to be stopped at the end. But now the time frame we choose is just 10 seconds, so it's not going to show up. Now, I would like to see the results for that. You can see the result again to achieve are going to be the following. Direction, the X and the Y, the theta, theta dot, and the theta double dot. So just double click on that. Sorry, I had. Okay, so these are the parameters we're going to achieve from the simulation. Just remember that you need to write down a discussion about that. Again, to make it in focus, click on that, everything will be set in position. If I would like to find the specific value for the parameter at a certain time, I can use the lens here. I can go to this position specifically, again, to make the selection, and you can see that it's going to be zoomed for every one of the graphs we have. So again, to get close to this position specifically, okay, and then that position. So every time we're going to click on it, we can find what will be the value at this position. So you can see here that this is the time. Okay, so this line is represent the time 3.279 seconds. And during that time, you will find out what will be the value for the top one, the theta double DD, which is the alpha. For the first one, actually, is not used. I mean, this one is not used. This is the Rx, this is the Ry in the Newton. Okay, and this will be the value for the omega, and this will be the value for the theta itself. Okay, so if I get to zoom out, I just need to put that back once again. You can see what's happened for the value for the theta. So it starts from the 35, is going to be swing down to negative 35, and keep doing that. Okay, just swinging. What's happened to the force is going to be changed from positive value to the maximum to a negative, and so on. Now, why these values are changing? Because the weight position will be changed. Okay, so it's going to become higher and lower as we go. The same thing is going to be for the Rx. The Rx is going to be pulled and pushed. So that's why it's going to be positive and negative alternatively. So that's what you need to find. You can change your parameters for 3 sets and make a comparison between the graphs if you want. Now, if I get to go within the brain reaction forces, again, we're going to have that shape. And I would like to get these value once again. It's already been simulated, but that's mean if I get to double click on that, I will get the graphs for the forces. So again, we can do the same thing as I told you. First thing to be is to scale it, and then you will see that. That's what we're going to achieve. Okay, so what else do we have? Again, I'm not explaining. I just show you how to go through the steps. Then the simulscape model. Well, we can see that we don't have results here unless we're going to go to the escape. So this is the escape, and you can see the reaction force has been calculated here, and the angle, position, and the velocity and the acceleration has been calculated in this block, which should be the same. And you can see that the last part is going to be making a comparison between both. Now, what will be the first thing you are going to notice with this simscape that different from the simscale or Simulink? What is the main difference you will find here in this graph? You remember last time we were zooming to the point to know what is the value, right? Now here you can see that we have these two lines. So I can find, for example, the difference between two different intervals. So I will put the slider here to the time 2, which is 2 seconds. And this will be at 1 second. And I will get the value exactly. I will get the value for the alpha, okay, in both positions. Delta time is, delta t and delta y is also being given. So that's for the theta. This is for the omega, and here's for the alpha. These are the parameters we have for this slide, because the one we selected here is mainly for the position of the theta. Here we're going to have the same thing for the forces. So yeah, it's more advanced. Maybe it's look more complicated, but actually there's a tutorial on the math space, which actually going to show you how to make your own. So again, we're scaling that. Again, at different times, you can find the value of the forces. Just drag it anywhere, or simply you can write down, I would like to know what will be the value for the forces in the position of, let's say, for a 5.15 seconds. Okay, just enter that, and it's going to tell you what is the value of the force in the y direction. You can change that to have it in the y direction or the theta in degree. So that's actually the advantage of the simscape, that you can have a discussion about it in your report. Now, in this model is going to make a comparison between the value has been gotten from both sides, and double click on that again. Okay, so actually this should be two graphs on the top of each other. Unfortunately, we cannot see them, but it can tell you they are compatible. Okay, now sorry, I spent something like 36 minutes talking about this model, and actually, if we need to move forward, because I don't want the video to be too long, and it's going to be actually quite boring. Just remember, here, I just want you to have the gut to go forward, open these files, and working on them. So we did the task 1 and 2. Now you can see for the task 3 and 4 are going to be a similar one, but we're going to have a friction at the top, and this will cause that the connection at the top will be sliding. It's not fixed, it's going to have friction, so it's going to be sliding. So remember that the force in the x direction was pulling the top pin. It's horizontal. So if we're going to have the y value, which represent the n normal force, and we're going to have the force horizontal going to overcome or within the same direction of the friction force, then we're going to have a different position for the work. So I'm going to close these two. I'm going to open the third one. Both scenarios are identical, so I'm only going to go through one of them. But I'm going to show you actually how they are going to look like. So that's a 3. We're going to have sliding block, and the other one we're going to have the sliding cylinder. The concept should be the same. So let's go through the block 1. Again, we're going to have the parameters we can update. I will leave this one as the original one. You remember that I changed the parameter in the previous one. You can see what we added here is going to be about the bricks parameters to be added. This is the pipe, and that's what we had in the previous block. And this will be the bricks, which is the part that will be sliding. Also, we can add some parameters about the coefficient of friction, and this will be done later. So again, this from the previous one, I need to clear it before again to start to do any work. And then I will refresh my command window. Okay, now again, I'm going to put that here and run this section to update my parameters. So new parameters are going to be defined. Now, define the initial condition, which is going to be about the theta. I will put the theta to 35, like what I've done last time. And this is updating that. Click on that, and we're going to have a new parameters to be added. Again. Okay. Now, if I would like to see if something has been happened here, I can change the view of my screen. So actually, nothing is happening here. I will leave this one for a while. Now we need to find the surface friction between the forklift forks and the block. So we define the coefficient of friction. You remember that we have the coefficient of friction for the static and the dynamics, and we have the critical force. The critical force is going to be the minimum required friction force, which will, if it's going to be overcame, the block will start to move. Okay, so we made that once again as we can change that from here if you would like to change them. And these are the forces to be calculated. I'll put this one here and update my system. Now a new parameter has been generated. Now we are going to go to the Simulink file. Just execute this section. We'll take you to the file, and then we are going to learn on how to change some of the parameters. The parameters you can change is going to be, if you're going to leave it, change the block mass, change the coefficient of frictions and the critical force as well, because this will tell you if I would like to prevent the sliding of the block, simply I can increase the coefficient of friction or increase the mass of either the cylinder or the block. So that's our model. You can remember that this part has been already imported from the Simscape. It's not, they are already one. And we are going to check exactly what will be the output we are going to achieve. So again, it's going to be reaction forces on the body, and we're going to have the velocities of the blocks. And this will be for the pipe. Okay, that's for the bricks. The other one for the pipe. Okay, so again, I'm going to run this simulation. Now you can see that the top is going to slide. It's not going to be about just moving from one direction. It's not about the swinging. I don't know why it doesn't work very well. We'll check that very soon. Maybe because it's moving, but I cannot see it moving.
It works on mine.
Sorry?
It's working on mine.
Yeah, I don't know why it didn't work with me. Oh, yeah, it's worked now. Sorry. So you can see it's moving as crazy. So why is going forward and backward? What's happening? Because you remember that the Rx value is changing position. So once it's going to push it to the left, second is going to push to the right. Okay, so now let's see what are the results we're going to achieve for the pipe. So this is not going to be different from the one that we saw earlier. Double click on that. Okay, so why the theta value is going that way, unlike the previous one? Because now it's moving. So it's going to be dropped down to a lower value as soon as possible. Okay, now once again, you can check, for example, different masses, and you will see that how these values are going to be changed. Four direction forces. Oh, come on. Okay, now that's similar to the one we had last time with the Simulink. Now you can see that the forces as well is going to be observed because we're not going to have a constant position. So you can see that at the beginning, in the first second, is going to be 8. Which one is that? The alpha, yeah. So the alpha is going to be 8.5. Sorry, we are recording, so I don't want to have your chat to be appeared in the video. Sorry for that. Okay, so you can see at the beginning the value was too small, and then it started to increase to 6,600 Newton after 13 seconds. Again, you can just keep sliding that and see what will be the value, the maximum value we can have for the Rx, for the Ry, sorry. So after 0.6 seconds, it's going to be, wait a second, I would like to have it exactly in position. So let's try with the 0 when it was still constant. Okay, and let's say that this one is going to be after 1 second. So you can get the parameters from here and make your own drawing. So for the second one, it's not going to be much different. It's almost the same, but the case is going to be a cylinder. Now let's see what we'll have in the case of the block at the top, the bricks one. Once again, we're going to have the position and the velocity, and it's being defined by this diagram. Okay, so you can see that this will be the x position, the velocity in the x, the pi position in the x, and the pi velocity in the x, the bricks position in the y, and the pi velocity and position in the y as well. And this will be in the z direction. So these are the results you would like to achieve from this one. You are going to repeat the same thing for the, no. Okay, you're going to repeat the same thing for the sliding number 4, where the part is going to have a cylindrical end instead of the block shape. Okay, so once again, the steps will be started by changing the parameters. Be sure that you're going to clear that by doing the clear and CLC. Then you change the parameters. You go to the end, click on here, change the theta, click here, and then define the service coefficient and the critical velocities and update that. Then you execute the Simulink code. Okay, so that's what we have for the task number 2. It's going to be quite long. So when you divide the work between you, for these sessions, just to be sure that each one of the students is going to have one of the long tasks. So it's not going to be end up like one of the students going to do this part and another long part while the other student going to take the short ones. Okay, so I'm going to stop the recording for the part number 1 here, and then we are going to go to the part number 2 and make another video for that. So where is the meeting? The meeting is here. So now I'm going to stop the recording and we're going to make a new one. So this will be part 1.